I'd like to share this project is a journey for the project team and AECOM team. AECOM team was appointed as the structural and the geotechnical consultant. So I'm going to walk the talk in our memory and the technical achievement and continue to complete the project by end of 2016. The title is called A New Level of Integration of Design and Construction Solutions. There are 7 aspects will be covered. Because of the time is short, so I'm trying to really give a snapshot of all the aspects. Dazhongli project is located in the downtown Shanghai with about 500,000 square meter construction floor areas. So it's a truly very large-scale, complex urban development. It includes 5 towers. Tower 1, Tower 2, there's 2 office towers. One is 150. Actually, the actual height is 170 tall, and the other office tower is 250-meter tall. You can see from the picture clearly. There are 3 hotel towers also on this site. There was Auditorium Building in a separate lot called Lot 46. There was a 23-meter tall, 3-story building, and there was an entire podium link all the towers together with 4 stories. The big basement, 4 levels, 22-meter deep. The entire entire basement level 1 is retail, and partial basement level 2 retail as well. So the project duration, you can see, long time, isn't it? It's very rare in China. Normally the speed, the pace of design construction. But this project really embodied lots of characteristics and challenges and the interesting part. This shows the master plan. You can see the different block, the locations. But the interesting characteristic, you can see the blue line, actually the metro line, called the Metro Line 13, running across the longitudinal side of the project. There is a new Nanjing West Road station is to be built alongside with this project. So you can see Tower 1, Tower 2, and associated basement is very much close to the new metro station. And the green line shows one of the oldest metro lines in Shanghai, Line 2, right cutting across the site. And we're going to build the 3-story auditorium building on top of it. Constraints of the project. Normally, almost the major development in the urban city will encounter lots of constraints and challenges. This one has no exception. First, the bigger constraint is metro criteria. We know anywhere near the metro tunnels, especially concurrent construction and design activities, the design side has to be, in Shanghai, has to be really co-work with the Metro Bureau, and we need to get all the criteria and approval from Metro Bureau, apart from all the necessary statutory submissions approvals. So in coordination with the Metro Bureau, so they set this stringent criteria. It's mainly include any vertical settlement induced by the construction work to the metro tunnel should not exceed 20 mm. And additional pressure induced to the metro tunnel shouldn't exceed 20 kPa. Relative bending moment caused to the tunnel shouldn't exceed 1/2,500, which is quite stringent, you can imagine. And vibration peak velocity caused by construction work shouldn't exceed 20 mm per second. So as I just mentioned, if we still remember that master plan, the Tower 1, Tower 2, and associated basement fall into the 50 meters adjacency of this metro tunnel, and also we have the building right on top of the old metro line. Another interesting characteristic on site is, if you see this is a very historical building, and there was a historical building reservation on this site as well. So originally located in this location, but right on the site. From the planning approval, it's allowed it to move this historical building to the new site, which is near the boundary of the site. So this is the building built in built in 1920s. It's called the Chew's Residence. And through the years of history, it has been used as a school. So the latest name we call the Min Li School. This building will be preserved on site. Later on will be the residential club and the retail house for this entire development. Another interesting constraint is we can see that this new metro station almost blocked the entire main road. It's called Shimen Yilu. And this one, we're going to build something with totally lots of activities as well. So there's no any temporary access and diversion of the site, to provide the public transportation and also for the site activities as well. So by considering all the constraints, the project decided to make this purple line as a temporary road. So the difficulty of this, the challenges thus provided to the project is it cuts the entire site into two parts. And there's lots of challenges. We had to replan the site logistics, accesses, and the construction activities. Also, we have to consider how to build this area in the future. Once the metro station is completed, we're going to move the temporary road back to the main formal road, and then we have to do the reinstate of this road, also build the basement below. Construction for such a major development has never been easy. It's talking about 500,000 square meters. So the phased construction program has been set since the very beginning. However, the activities is ever changing, but it will follow the main time frame. 3 major phases. Phase 1 is for the 2 office towers and associated basement area. Phase 2 is for the hotel. There's one here, one there, and another one there for the hotel buildings. So phase 3 is for the entire building and the annex buildings associated. 13 subdivided zones, you can see all the different colors, with detailed time and activity plans. So the entire project actually follow this one sheet, colored sheet program, and very much so, we've been working on it over 10 years. Let's look at the structural side. I'm not going to talk about too much on the hotel buildings because those are relatively low, 70 meters height. I'm focusing on the both tall towers, Tower 1 and 2. Tower 1, 34 stories, 153 meter tall. That's the main roof. We still have steel features on top. Tower 2 is 250 meter tall, 52 stories, 4.2 floor-to-floor height. The structure system, you can see the architectural plan, and the structure system is very much kind of conventional, reinforced concrete core wall, and perimeter column system. Composite floor with steel beam and reinforced concrete slab. From the stability point of view, we actually introduced outrigger and a belt transistor for the lower tower, Tower 1, for the one location at level 20. For the taller towers, we introduced the 2. One is at a level 21 at the mezzanine floor, also at the level 36 to 38. So this is the typical Tower 1 framing. You see it very much similar. However, the loading, and because the clients are tenant renting strategies are different. So the 2 towers actually got to be all separately designed, all separately considered. And this is the outrigger and the belt truss profile. This is for the Tower 2. Seismic sections. We know seismic design to lots of designers. If it's not domestically trained engineers, it's very mysterious and also it's difficult. For this project, for these two tall towers, actually, there was a seismic control, not wind control. Therefore, seismic actions, we're going to look at it very carefully. Any project, we're going to do seismic safety appraisal report. It will provide certain parameters like peak acceleration, ground motion, define the site categories, and this the site typical period, and the structural frequency reduction factors. So we also look at the national code and the Shanghai code. So apparently, if you look at the spectrum, the blue line is the Shanghai code, the red line is national code, and this is 50 years recurrence, this is 100 years recurrence. I'm sorry for the Chinese, we haven't really put it into English. So you can see the blue line is still the control. And we're talking about for instance, the lower tower, the structure period is very much 3.6 seconds, and the taller tower is very much 5.6 to 5.8 seconds. So it's very much this blue line control, which is the Shanghai local code control. First of all, the design started with elastic analysis. So both towers was working on this aspect. We used the two different softwares. So the typical mainland popularly used the PKPM sideway software, and also the ETAPS was used. I'm not going to read through all the detailed numbers. You can see the paper from the proceedings. So basically, all the interflow drift control for the tower 1 is 1 over 800. For tower 2 is 1 over 500. So from the tower 1, tower 2 figure, you can see it's all meet this requirement. For tower 2, which is taller, so we further get into this nonlinear elastic plastic history analysis and the severe earthquake. Yes, we have done the frequent seismic analysis and the fortification level of seismic analysis. Both are approved, are in the good shape, and the structure really presented the sound solution. For this one, you can see this is the typical inter-story drift. And we adopted the different time history. There was 2 natural time histories, different colors, and 1 artificial time history. You can see all the profiles within this code limit with 1 over 100. Again, also for the tall tower, shaking table test was conducted. That was very much in 2010 and early 2011. And the result actually verifies the design solutions. Of course, recommended we need to increase the ductilities of the shear walls and the lintel beams. So the design has been refined, and very much the construction drawings was also done and approved. Wind tunnel test for the entire site as well. So you can see, and that provided the wind pressures for structure and also for curtain wall design. I need to give a little background. So this is for Tower 1. The Tower 1 analysis, and the title is wrong too. I'm terribly sorry. I don't know why it comes like that. This is for Tower 1. We experienced the significant design change after we have done all the design, construction drawings approved. So early this year, the clients decided on a commercial decision, they got to add 1 story, 1 floor into Tower 1 within the same height. So we reduced from 4.2 floor height to 4.1. So in order to squeeze this 4.1 meter and add it back into the building. In the meantime, there's equipment room changes, water tank moved to the different levels, and the refuge floor changes as well. So this process is not just rerun the model, see it's okay, it's simple like that, structure all meet all the numbers. Actually, it is a reconsideration of design optimization. So what we have done in summary is we found from the time history analysis, we found the original level 20 outrigger and belt truss location is no longer good enough for the building in terms of performance. So we moved one level up to balance the stiffness distribution. So you see that this become, I'm sorry, seems equipment not working. You can see there was a little jerk there. You can demonstrate that it really shows it moved the building, the deformation back. And this one also, the y direction of interflow drift is all within the code limit. The other one is we supplement, because this building has been improved, gone through all the seismic expert panel approval. So once we change it, and the code upgraded too, the Shanghai code in 2013. So all has been taken into account as a new building to adopt all the new changes. So we have to do the reanalysis. This time we supplement the time history, elastic plastic time history analysis. Here, this one shows we not only done the elastic plastic time history, also supplemented the elastic time history analysis. So we plotted these two curves all together. This is the base shear. You can see, because of the building itself is relatively stiff, so you can see the blue line, the elastic, and the elastic plastic the energy doesn't dissipate very much, very significantly. So it's also the analysis proves this is a relatively stiff building. What we have done is we trying to tune down the outrigger and the belt truss. We tried to delete the outriggers, but it was not very good for the entire performance. So we keep them, but also tune down the steel tonnage and reduce it to put in more, reduce the stiffness particularly, so to balance the overall structural performance, and of course reduce the steel tonnage, in turn reduce the cost. And we looked into the wall, the shear wall profile as well. This collected the ductility, and it shows that if, like, when this is the natural time history, one of the natural time history. When it goes to 10 seconds, the building is still elastic. So it's all in blue. When it goes to the 35 second, 40 second, you can see some elastic plastic behavior comes onto the wall. And this shows us the ratio of the actual deformation and the elastic plastic deformation ratio. So you can see some areas developed the plastic status for the wall itself. Also, if you look at the spatial area, the specific analysis we have done is for the level 2 with the bigger opening on this side. Actually, one slab, the slab is very much on one side, and there is a 2-story height. So the slab thickness, we optimize this. We think we got to be increase the slab thickness while reduce the rebar ratio, and then provide enough stiffness and balance the stresses inside. Again, there is on the roof, there is a little transfer area because the floor plate got to be reduced a bit. So we add in this steel beam and put it in the transfer beam and the steel column to support the higher level floor plate. Again, the transfer beam and the column has been carefully checked. This time on the safe side, we considered the vertical seismic load. Normally you don't need to consider, but we consider this as major and important structure element. Again, we talk about the settlement, the material criteria. So on this project, we have done the significant soil analysis or settlement analysis. We use the Plexus 2D, 3D analysis to consider the impact of the tower, both tower construction to the metro tunnel. So this is the Tower 1, and this is analysis for Tower 2. The conclusion is because as I mentioned, the time program changes forever. So when we did the early program, and the time's really delayed. When the construction time delayed, especially the metro station construction time delays, and we look at the Tower 1 construction time change as well. So initially, we concluded this was a 19 mm vertical settlement. So it's very, very close to 20 mm, but still within the criteria. And later on, we verified it and it would be 18 mm. So because of the tower construction advanced, the metro station construction delayed a bit. So actually, this will help the release the little settlement onto the metro tunnel. This is Tower 2. Tower 2, the impact actually is more significant. Actually, it's reduced from the total settlement of 16.4 mm compared with the previously, or the initially analyzes the nearly 19 millimeter. So those designs all been scrutinized, approved, agreed with the Metro Bureau, and also, of course, gone through the statutory submissions. Looking into the second constraint is the school relocation, the existing building relocation. This is very 1920s building. You can see some framework, some masonry load-bearing wall system. And there is a timber truss, timber floor, and partially some concrete roof structure. And also the footing is very much concrete plains and on the timber piles. So to move this building is not easy. Yes, the clients involved, the specialist consultant, are working with the entire team. So the conclusion is the inclined street line from the original location to the new location, and that's the solution. To do so is first you have to strengthen the existing building. There's two pictures, so you got to strengthen different part of the building first, and then they got to build the top supporting beam inside the building. Also, they got to build the bottom supporting beam outside the building, form the track. So on both of that, you have a hydraulic tracking and pulling system in order to move it. Of course, in the new location, you have to build the foundations. So we designed the new foundation system there. Once the building is located, you got to sit on top of it and then connect them together. I show you some of the real pictures. This is 2009. That's the actual building strengthening work. And this is the building inside. They put the top supporting beam. And this is working on the outside of the building to put in the bottom supporting beams. And this is also the preparation for the central frame area. And that's the construction process. Eventually, you see this is the original location where the original building is. And this is on the way, move, and then it's finally located. The entire process lasts a very short period of time. Remember, it's 2 weeks' time. Auditorium building sitting on top of the metro line. So we designed it as a steel structure. So steel frame structure with a composite floor system. And everybody worried, this is the auditorium building. Yes, the vibration transition is significant. Therefore, the professional consultant was brought in, provide vibration acoustic consultancy as well. So eventually the solution is there's two round circle tunnels. And we got to carefully location the piles and the columns. And also we introduced a stream box proprietary product, put under the column, so to provide this anti-vibration system. Again, the raft pile construction is not straightforward. Entire design you can do easily on the paper, but in reality, design and build have to cut it into 59 numbers of pieces. And the construction is you have to do it only at a special time slot from midnight to 6 o'clock in the morning. And then you got to test it. Also, you got to monitor all the site monitor about the ground movement, the metro tunnel movement, and the adjacent building movement as well. So this is some pictures showing our guys sitting there. We are really midnight working on site. top-down construction for the temporary road area, as we just mentioned. So this is the sequence of the top-down construction. And also designers and contractors, we are very much work hand in hand to develop this top-down strategy and the design solutions. I'm not going through in the detail. You can see it's very complex and a very, very dynamic process. This is the construction pictures as well. Conclusion is AECOM not only work on the design side, also we deploy a full team of nearly 15, 16 number of site people concurrently working on this site. They provide the eyes and the ears and the hands on site to help the entire project team, and also liaise with contractors, really pulling everything together. So this is the extremely dynamic project with very enthusiastic and ever-contributing team. So this is, nowadays, we are not just a linear design process. You design, finish, and the construction, so designers finished. Actually, we have been involved in the past 11 years for every bit and piece of design and construction. So thinking of constructability at the very beginning, make it a workable, practical design, I think that is the challenge for today's vertical urbanism. The last minute, I'm going to make this acknowledgement and appreciation for the entire team. I haven't listed them all, but those are the really closely work partners. And there was many very, very long on the list. I'm sure the clients someday will present it to all. Thank you very much. Thank you.